Hi, I am Devendra Narade. In this video, I am going to cover implementation of runtime type information. RTTI is used to get type information about an object at runtime using pointer or references. Compiler writes code for RTTI with the help of virtual functions and virtual table. When we create an object of a class, first 4 bytes will be a virtual pointer which points to the virtual table, and the first 4 bytes of the virtual table is related to RTTI. There are two main applications of RTTI, type ID and dynamic cast. We are going to cover both of them one by one. The implementation of RTTI is specific to compiler writer. C++ provides a way to get type information of a class at runtime using type ID operator. We can use type ID operator as many times as we want in our program, but it will point to only one type info structure which is unique to the class. Conceptually, when we create an object of class A, compiler adds RTTI information to the class's object, and we can get this information using the type ID operator. Let's take an example how RTTI uses type information stored in objects by the compiler to determine at runtime the actual type of an object pointed or referred to. In order to demonstrate it, I am going to use this class relationship where class C is derived from class A and class B. In order to use RTTI, your inheritance graph should be polymorphic, which means you should at least have one virtual function in your base class. In this class A, I have two virtual functions foo1 and foo2 with data member A. In class B, I have foo3 and foo4 as virtual functions and data member B. Class C is publicly derived from class A and B, which overrides function 2 and foo4. When compiler sees there is a virtual function in your class, it creates a virtual table corresponding to that class. Virtual function table is a table of function pointers pointing to the definitions of virtual functions. When we create an object of class A, the first 4 bytes of that object will point to a virtual table. This bit is called virtual pointer. In this virtual table, second entry is an address to first virtual function foo1, and the third entry is an address to virtual function foo2. Similarly, when we create an object of class B, its object's first 4 bytes will point to B class's virtual table. The second entry is foo3 and third entry is an address of function foo4. In order to create an object of class C which is derived from class A and B, we inherit the memory model of class A into our memory of class C. Then we inherit the memory model of class B into C's memory. Then we put other data members of class C. Virtual pointer A points to a copy of A's virtual table. Virtual pointer B points to a copy of B's virtual table. Right now, A's virtual table is pointing to the definition of class A's function, and B's virtual table is pointing to the definition of B class's virtual function. Now compiler sees that you have overridden foo2 function, then it removes this link and updates the address of C. Similarly, compiler sees that you have overridden the function foo4 as well. It finds the function foo4 in B table and it removes the link to the definition which was pointing to the class B. Now it updates the address to C's foo function. Compiler uses the same virtual table in order to navigate to classes type information. You can see that the first 4 bytes of virtual table is an address to RTTI structure. The C++ language has provided a mechanism in order to get the address of RTTI structure, which is type ID operator. When we use this operator at runtime, we get the hold of virtual pointer, which points to the second entry in virtual table. Depending on where we are in inheritance hierarchy, a thunk is added or subtracted to virtual pointer. In this case, we have to subtract 4 bytes in order to get the address of this type info structure. Compiler creates the same inheritance graph as it was created for class hierarchy. The type info for derived class is also derived from the type info of class A and class B. Type info class has two interesting members. First one is name. Name is used by type ID operator. This member function returns constant character pointer. In classes A scenario, it is going to return string A. Another interesting member is basis. It maintains a list of base classes. In case of derived class type info, basis has two members. First element points to the type info of class A. Second element points to the type info of class B. Basis data structure is useful for casting at runtime when we dynamically determine the data type of a class and we want to downcast from base class to derived class. This data structure is used to determine the validity of inheritance hierarchy. Dynamic cast is an application of RTTI. We will see how dynamic cast performs downcasting, and we will also see how static cast performs downcasting. Downcasting is an operation when a pointer to a base class or an indirect base class is converted into a derived class pointer. The syntax for static cast and dynamic cast are same, but the result of static cast is that the expression is converted into a pointer to a specified type, converting a static type pointer into another type of pointer. Whereas dynamic cast operator relies on the information stored in the objects by the compiler associated with the base class or the derived class. The expression is converted to a pointer to the specified type if the dynamic type of the object pointed to is of that type or the type of the derived class. Otherwise, the result is 0. Let's have a look at an example of downcasting. We create an object of class C and assign the address of object C to the base class pointer. Now I use dynamic cast to convert base class pointer into derived class pointer. As you can recall from my previous screen that RTTI structure has basis data structure which keeps track of all the base classes in it. So it can clearly see the derived class C has two base classes. The pointer to be converted falls under this inheritance graph. So it is valid conversion and it returns pointer to the derived class. Let's create an object of class D which is not in this inheritance graph. We create an object of class D and assign the address of object D into base class pointer. Now we use dynamic cast to convert base class pointer into derived class pointer. Now again RTTI uses its basis data structure to find the base classes. The pointer A is pointing to the class D. It looks for the base classes of D. It doesn't have any base classes which are class A or class B. So it is invalid and it returns 0. Thank you very much for watching this video. If you like, please subscribe to my channel. Thank you very much.